Hello, my name's Chris Mack, and this is a presentation I gave last week at the SPIE Advanced Lithography Symposium in San Jose. I'm going to try and give as close a facsimile to that presentation recorded here now as a sort of a record of what I said. I can't, of course, do it exactly, but it's pretty much the same. The name of the talk is More Systematic Errors in the Measurement of Power Spectral Density. 2 years ago at this conference, I gave a lecture on spectral densities, power spectral densities, how to measure them, and I talked about both random and systematic errors that are built into the measurement process. From that, I derived 4 important lessons for how to do a good job of measuring the power spectral density of a rough lithographic feature. These lessons I'll repeat here before going on to mentioning a few more that I've learned in the last few years. First, when measuring the line edge roughness or the line width roughness of a lithographic feature, it takes 3 numbers to characterize that roughness. Those numbers are the standard deviation of the edge or width, what we call the line width roughness or line edge roughness, sigma, the correlation length, and the roughness exponent. All 3 of those parameters are needed to describe not just the magnitude of the roughness, but its frequency content as well. Measuring PSDs is a very noisy business, and therefore to get reasonable statistics we need to average as many PSDs together as we can. The best results I've seen are well over 100 PSDs averaged together. I've seen people publish results in the 200, 250 range, and that produces some pretty good PSDs. If you only take one or a handful of PSDs, you're going to have a very noisy result. Data windowing will reduce spectral leakage to very small levels and is almost a requirement to do a good job. I'll talk more about data windowing in this lecture as well. And finally, the 4th lesson from my talk a few years ago. Because of averaging that occurs when an SEM interacts with the sample, the interaction size, the blur of the SEM within the sample averages out some of the smoothness, and you can use that to counteract the effects of aliasing. So the best way to do that is to set the sample grid, the distance between measurement points along the line, to be 2 times the interaction size, full width, half max. That will produce a PSD which is valid out to about 80% of the frequency range before aliasing starts to take over. All of these results can be found in the publication shown at the bottom of the slide. Now I'd like to talk about a few more lessons, and the first one has to do with the random error, the noise that's inherent in the measurement of a PSD. Since every rough line is unique, every PSD that we extract from a rough line is also unique. Only when you average a large number of these things do you approach the true PSD of the underlying process. We can in fact quantify the uncertainty in a PSD measurement mathematically with some assumptions about the underlying probabilities, but we find that the uncertainty, the standard deviation of any given data point, say this data point here or this PSD value at this frequency here, the standard deviation of that equals the mean value of that PSD. In other words, the relative uncertainty is 1 or 100%. That is a lot of error. When you have 100% error in every data point, it makes you wonder how much information is really there. But in fact, there is information. But it's so noisy that it's hard to really see what that information looks like unless we do some averaging. Here I show a noisy PSD, and here's what happens when you take 10 PSDs and average them together. So if I had 10 different features and I measured them and extracted PSDs for each one of them, average them together, I get something like this. You can see we're beginning to see the underlying shape of the PSD much more clearly. Of course, I'm showing you in the red line what the true value is, so it helps the eye. If I average 100 together, you see the noise levels have gone down substantially. In fact, The relative uncertainty then becomes 1 over the square root of m, where m is the number of PSDs that you've averaged together. So if you average 100 together, you reduce the uncertainty by a factor of 10. That gets us down to about 10%, 1 sigma uncertainty in each PSD data point, which is now getting to be, I would call it, reasonable. Of course, I'd love to have more PSDs averaged together as well. Well, we can quantify this uncertainty a little bit more by adding error bars to our data points. We know if we average m of these PSDs together, then each PSD data point will be chi-squared distributed with degrees of freedom equal to 2 times m, where m is the number of PSDs we've averaged together. That allows us to put error bars on every data point. The error bars will be best described by a confidence interval, very standard statistics confidence interval, because we know the underlying distribution is chi-square. We say that the true PSD value, which we don't know, is somewhere in the range of these two numbers. These numbers are the degrees of freedom multiplied by the measurement value, the number I got from the average of all the PSDs, then divided by the critical value of chi-square. If alpha is the significance level, for example 0.05 for a 95% confidence interval, then we simply look up in a table or calculate in Excel or something the two critical values for chi-square, and we have our confidence intervals that we can use to make up our error bars. And here are a couple of examples of that. Now, the chi-square distribution is asymmetric, and as a result, our error bars are asymmetric. Most of the errors occur below the mean value, the true value of the PSD, and therefore our error bars are tilted up, where there's more space in the upper side of the error bar. You can see these error bars are quite large when I only have one PSD. Now, is it important to add error bars to your graph? Well, let's just look at this m equal to 1 case. What does this data tell me? Well, you might imagine this is kind of a fractal behavior, a linear behavior on this curve up to a point, and then it looks like it's flattening off. But can you really tell that? It's very noisy. If I add the error bars, I can see that it's possible that straight line or fractal behavior will occur all the way through the frequency range. And in fact, I can't really draw a conclusion that the PSD has leveled off at the lower frequencies when I see how big these error bars are. Now we can calculate error bars for the case of m equal to 25, and we see that these error bars have shrunk dramatically, and as a result I can look at this and with some confidence say, yes, the PSD is flattening out at low frequencies. Also note that these error bars are a fraction or a percentage of the nominal or true value. As a result, since I'm plotting these graphs on a logarithmic scale, the length of the error bars on this logarithmic scale is the same for every data point. That means I don't have to plot error bars on every data point. They all have the exact same length. Therefore, I can plot error bars on only one data point, and that's good enough. I can visually see what those error bars will look like everywhere else. So my recommendation is to, plot the error bars just on this lowest frequency first data point, and then you'll see what the uncertainty is for everything else. So lesson number 1, always use error bars on measured PSD graphs to help prevent overinterpretation. Another problem that I talked about in my paper a couple of years ago was the problems of aliasing and leakage that is inherent from the fact that we're sampling a finite sized length of line when calculating our PSD. Now, for the case of a roughness exponent of 0.5, I was able to derive analytically what these leakage and aliasing factors are. And leakage in particular is controlled by the ratio of the correlation length to the length of the measured line. So a longer line bigger L will result in less leakage. Here is a plot for the case of h equal to 0.5 of how much aliasing and how much leakage we actually experience. Now let's take a look at these numbers. Aliasing is 0 at 0 frequency, but it rises rapidly, and you see that at the higher frequencies the amount of aliasing becomes huge, 150%, so that the true value, the measured value is 2.5 times the true value. That's a very, very large error. It's a big problem at these higher frequencies. Leakage, on the other hand, looks pretty small. You see it's only about 4% for the conditions that I'm demonstrating here. Well, 4% is certainly in the noise of the aliasing error, except that's only true for h equal to 0.5. As the roughness exponent gets larger, the effects of leakage get larger as well. So we see for h of 0.9, which is the kind of roughness exponents we see in the after etch line widths and line width edge roughnesses that are observed, we see we can get up to 50% leakage error, which is a very significant amount, something that can't be ignored. So what do we do about leakage? Well, it turns out there's something we can do that works really well. It's called data windowing. Normally, we think of a very long line, and we measure this line by taking some segment of L length and sampling it to make our measurements. Then we process this data to extract the PSD. We can think of the measurement process as applying a rectangular measurement window. This rectangular measurement window has a weight of 0 for all data outside of this segment, L, and then weights all the data uniformly with a weighting of 1 within that region. But that's not the only measurement window we could use, a weighting of the data. For example, the Bartlett window or triangular window weights the data something like this. The point right in the middle is weighted fully, but then we weight less and less out to the edges of the same length segment L, and in fact the weight goes to 0 all the way out at the edge. By weighting each measurement value by the window function before calculating the PSD, we can dramatically reduce the spectral leakage. There's lots of different shapes of these windows. I mentioned the Bartlett window, which is triangular. The Welch window is a parabolic weighting, and then many of these others, Blackman, Hahn, Hamming, are sinusoidal in shape. They're all symmetric about the middle, and they produce slightly different results. Here I compare a number of different windows for the case of h equal to 0.5, and I observe that the Welch window produces the smallest amount of leakage. Now they all produce, an order of magnitude less leakage than we saw before, and for all of these cases the leakage goes to 0 out at the high frequencies, which is really good. As a result, any of these windows would be better than a rectangular window by a long shot. Nonetheless, the Welch window works the best for this kind of PSD data, so I recommend using the Welch window every time you measure a PSD. Now, another issue to worry about is something called detrending. Ideally, if we were going to make a measurement of line width roughness, that's the deviation between the measured line width and the true line width, we would need to know the true line width. That is, the mean value of the line width for an infinitely long line. Unfortunately, we don't know that. So instead, we subtract off the sample mean. That is, for the measurement that I made, I create a mean value of the CD, and then I look at the line width roughness as the difference between the measured line width and this mean CD. This is an example of detrending, where I take out, in this case, a mean value. The impact of detrending on the PSD is very simple. It forces the zero frequency PSD to be 0. That is, there's no information about the zero frequency, which is the mean value of an infinitely long line, because I don't measure out to infinitely long line. Now when we measure the line edge roughness, we have to detrend even more. We we have to subtract out a linear best fit edge position. Ideally, I might know where the true edge was supposed to be, and then I measure the actual edge compared to that true edge, but in reality I never know what the true or ideal edge position really was, so I estimate it by fitting a straight line through the data and then look at the deviation of the actual data from this best fit line. Well, what's the impact of this detrending on line edge roughness? Well, we can see qualitatively what it will be, and then I'll try to quantify it in a moment by looking at this simple example. Here's some roughness data, and when I look at it, I see a trend, a linear trend. Maybe the SEM image has been rotated a little bit. So I best fit the line shown in the red, and then I subtract the measured values from the best fit line, and that becomes my line edge deviation data. But in reality, this segment of line is in fact the first 25% of the line shown in the bottom curve. And what am I missing? Well, there's this low frequency undulation and high frequency errors are on top of that. And by taking the first 25% and fitting a straight line, what I'm doing is subtracting out a low frequency component. By using a linear detrending, I'm removing some low frequency information from the data. What will that do to the PSD? Well, we can see very clearly, because in simulation I have the unique ability to know where the edge was supposed to be. And I can in fact calculate the PSD without detrending. When I do that, I find that there is a systematic error. In the blue I have the PSD without the linear detrending, and in the red I show the PSD with the detrending, and you see that there's a 30% error. The detrending causes a loss of low frequency information, and my PSD goes down by about 30% at the lowest frequency. If I look at the error as a function of frequency on a log-log scale, I find that it follows a straight line behavior. That is, until it reaches the noise limit of my simulations. Here I average something like 10 to the 8th different PSD simulations together. But because m is 10 to the 8th, when I look at square root of 2 over 10 to the 8th, I find that there's a noise floor shown in the green line. And once I reach that level of noise, then I can't really see anything. But for errors larger than the noise floor, I see a perfectly linear trend on this graph. The dotted line is in fact my model for the detrending error. And I'll say that the linearly detrended PSD equals the true discrete PSD times 1 minus this linear error term, linear detrending error term. And the linear detrending error term goes as 1 over the frequency squared. In fact, it's 1 over pi times f times L, quantity squared, where L is the length of the line. Now, the lowest frequency that I can measure is f equals 1 over L. So at that low frequency, I find that the linear detrending error is 1 over pi, or about 30%. For higher frequencies, it goes down. For example, when f equals 2 over L, I find the linear detrending error is 1 over 4 pi, which is about a 12th, or about an 8% error. Maybe still noticeable if I've averaged enough PSDs together. But certainly the 30% error is going to be significant whenever I'm averaging 10 or more PSDs together. So what can we do about this? Well, one thing we could do is not use a rectangular window. I've already told you we should always use something like the Welch window. And in fact, when I run simulations for the case of a Welch data window, I find that the fall off with frequency is much steeper. It goes as 1 over the frequency to the 5th power instead of the 2nd power. Well, this is an advantage, certainly for all the higher frequencies, but still, when f is at its lowest, when f equals 1 over L, that power doesn't matter. I still get that same 30% error for the lowest frequency. We need something else to get rid of this linear detrending error. And the way we do, but before I tell you how we're going to do that, let me talk about one last thing. I always get ahead of myself. One other thing we need to worry about is when we calculate the AutoCovariance function. Now, most people calculate the power spectral density as a way of describing the frequency behavior of my roughness. But an alternate approach is to calculate the AutoCovariance function. The two are related because the AutoCovariance function is nothing more than the Fourier transform of the PSD. Still, some people will calculate the AutoCovariance function and plot it up. And without detrending, I might have an AutoCovariance function that looks like this blue line up at the top. You see, it's always positive. But by detrending, subtracting the sample mean, for example, or subtracting a best fit line for line edge roughness, I push all of these curves down, and in fact, I cross zero. My AutoCovariance function will cross zero. For subtracting off the best fit line, it crosses zero, goes negative, crosses zero again, goes positive, and then comes back down to zero. It looks like there's some oscillation going on, which might give you some idea of some interesting behavior, but in fact, it's simply an artifact of the detrending. So whenever you look at AutoCovariance functions, you have to be very, very careful, because unlike the PSD, where the errors are confined to the lowest frequencies, the errors for the AutoCovariance function are spread out over the entire lag distances. But there's something we can do to help with this problem. When we detrend, we don't have to detrend one edge at a time. It's very common to make a measurement of multiple features in one SEM image. Here I show an SEM image with 3 features. Each feature could be analyzed separately. If I'm performing line edge roughness measurements, for example, I could fit a straight line to this edge and calculate the deviation about that edge and get a PSD. I could fit a line to this edge, calculate the deviation about that best fit line, and get a PSD. I could get 6 PSDs and average them together here. But I'm losing something, some important information, if I fit a straight line to each of these edges individually. Why? Because when I built the mask and printed this, I know ahead of time that all these lines are parallel. I built parallel lines on my mask, and so when they print, they should be parallel. When I detrend, I could detrend them all together. I could find one best fit slope for all 6 edges. So when I fit a line, I could have a different intercept for every edge, but only one slope to fit them all. It's the equivalent of saying I'm going to rotate the SEM, subtract out some unknown rotational error in my SEM image, but rotating all of the edges together. What this means is my linear detrending error is reduced by a factor of 1 over k when I have k edges per image. This can be pretty significant. If, for example, I have 6 edges, shown here, I get 1/6 the amount of error. For the lowest frequency, that instead of being about a 30% error, that translates into about a 5% error, which is usually small enough to be negligible given the amount of noise I have in my PSDs anyways. I'd have to average together 200 SEMs or more to be sensitive to a 5% error. So, our lesson here, detrend 4 or more edges, or 6 even better, together when measuring the LER to eliminate this detrending systematic error at the lowest frequencies. So what are my 3 new lessons for PSD metrology? Number 1, always use Airbars on a measured PSD graph. That helps prevent overinterpretation. It helps explain your data better to anybody who might be looking at that graph. So I recommend that we always use Airbars every time we present PSD information. We should always use data windowing when measuring the PSD. I use the Welch window. Of the windows I've tested, that works the best. When we're measuring LER, line edge roughness, we should detrend as many edges as we can together. 4 or more is preferred. Of course, every feature will tend to have at least 2, and that's better than nothing, but if we can get 4 or 6 edges together, we can improve things significantly. All of these lessons learned should become industry best practices. They are, I think, not always very common in our industry, but we should start using all 3 of these techniques every single time we measure and display PSD information. Finally, there's still some future work. There's other techniques for extracting estimates of the PSD from data, and I hope to explore some of these in the future. Thank you.